Hello everyone. We have a question which says that a block of mass 5 kg over here is held in equilibrium. So the condition is an equilibrium condition near a vertical wall. Yes, it is a vertical wall by two light strings. The two strings are this one, and a horizontal force of magnitude x Newton, and this x Newton force is basically a horizontal force as shown in the diagram. The two strings are both inclined at 60 degree to the vertical. So both these two strings are inclined at an angle of 60 degree to the vertical. Very clear diagram with the statement. Given that x is equals to 100, find the tension in the lower string. They have given us the value of x, which is 100, and we have to find the tension in the lower string, this one, and the condition is an equilibrium condition. Equilibrium means opposite forces are equal, and when we say the opposite forces are equal, that means the opposite horizontal forces are equal as well as the opposite vertical forces are equal. For that, we have to split them up into horizontal and vertical component. But before that, we have to understand what the horizontal and vertical components are. I have seen most of the students have a misconception that the horizontal component is always a cos component. No, it is not like that. It depends upon the angle. If the angle is with the x-axis, then definitely the side next to that would be a cos component of that particular force, and the opposite side would be a sine component of that particular force. But if the angle is with the y-axis, then the side next to that would be a cos component of that particular force, and the opposite would be a sine component of that particular force. So basically it depends upon the angle. Based on that, you could easily work out which side would be a cos component and which side would be a sine component. So according to the question in the A part, x is equals to 100, find the tension in the lower string. So this value of x is 100 and the mass of the block is 5 kg, and we know that weight is equals to mg. So m is 5, g is 10, so 5 times 10 is 15 Newton. This is the weight of the block, definitely pointing downward. After splitting up the components of the given forces, the tension in the upper string over here, I have represented it by Tu, and the lower string I have represented it by TL, and we have to find the value of this TL as mentioned in the question. So the components, because the 60 degree is with the vertical, so this would be a cos component, so Tu cos 60, and this would be Tu sine. Similarly over here as well, 60 degrees with the vertical, so this would be cos component, so TL is a force, so TL cos 60 pointing downward, and TL sine 60 is the horizontal force. Because the condition is an equilibrium condition, that means the opposite forces are equal for both horizontal and vertical. So we would work out for both horizontal and vertical. First of all, if we just look at the horizontal forces and look at the diagram, we can see that we have two forces over here. Horizontal forces which are pointing to the left, and x Newton is a force, again a horizontal force pointing to the right. So the sum of these two, Tu sine 60 plus TL sine 60, as I have mentioned over here, would be equal to x, but x given in the A part is 100, would be equal to 100. Writing the value of sine 60 as 0.866, sine 60 as 0.866 with Tu and TL equal to 100. This is our equation 1 based on horizontal forces. And based on vertical forces, if we just look at the vertical forces, we have a vertical force pointing upward as Tu cos 60, and we have two forces pointing downward, which is TL cos 60 and 50 Newton. That means the sum of these two would be equal to Tu cos 60. So TL cos 60 plus 50 would be equal to Tu cos 60. Writing the value of cos 60 as 0.5, cos 60 at 0.5, we have a we have an equation, we could simplify this equation and make it more easier. So for that, just divide the complete equation by 0.5. So if we're dividing by 0.5 over here, we are just left with TL. 50 divided by 0.5 would be 100, and over here divided by 0.5 would be just left with TU. So we have a very simple equation in terms of TU, and that is equation 2. That means TU is equal to TL plus 100. In the A part, we just have to find the tension in the lower string. So what we have to do, we will equate both the equations, the equation 1 as well as the equation 2. The equation 1 is 0.866 TU, but our target is to get the value of the tension in the lower string. That means we have to find the value of TL. Just place the value of TU, which is TL plus 100 over here. So 0.866 multiplied by TU, 0.86 multiplied by TU, but TU is TL plus 100, and the same remaining would be same, that is 0.866 TL equal 100, and that is same. And if you just look at the equation is completely in the form of TL. Just open up the bracket, multiply each and everything by using the basic algebra and solve it and get the value of TL, which is equals to 7.74 Newton. So this was the answer for the tension in the lower string for the A part. In the B part, they have written us that find the least value of X. Least value of X, and the condition that they have given us is that for which the block remains in equilibrium in the position. That means this X should be the minimum. This X should be the minimum, that means the least, but the condition should be same, and that should be the equilibrium condition. And for the equilibrium condition, this block should remain over here. But we know that if we just lower up this force, definitely a time would come when this block would definitely move down, and when this block would move down, then the tension in this string, in the lower string, would end up, it would become 0, and definitely there would be no tension if we reduce this force, which is the X Newton force, because according to the statement find the least value of X, so we have to find the minimum value of X for this, so that the condition remains in equilibrium. For definitely for that condition to get the least value, we have to consider that when we go for least value, definitely the tension in the lower wire would finish, and that tension would be 0. So in the diagram, the tension over here is finished, the TL would be 0 because of the condition of the least value, and we are just left with these forces, the upper one, the tension in the upper string, and the component based on that. These components are of no use because the tension over here is 0 now. Now simply focus on this diagram, the upper one, the tension in the upper string, and this X, and make up a condition based on equilibrium for horizontal as well as for vertical. That means for horizontal forces, now we can say that simply TU sine 60 degree would be equal to X, because both are horizontal and in opposite direction. So TU sine 60 would be equal to X, and X is equals to TU sine 60. Sine 60 is 0.866 times TU. This is our equation 1. Similarly, for vertical also, we have just TU cos 60, which is pointing upward, and a 50 Newton, which is the weight of the block, pointing downward. The condition is an equilibrium. That means the opposite forces would be equal. That means TU cos 60 would be equal to 50, and over here cos 60 is 0.5, TU is equals to 50. And after that, from here we can say that TU is equal to 50 divided by 0.5, and we have the value of TU as 100 Newton. Now substitute this value of TU as 100 Newton over here in this first equation and multiply that by 0.866. You will get the value of X. So we have done the same. We have used this value of TU 100 placed it over here, multiplied by 0.866 like over here, and finally we have got the value of x as 86.6 Newton, which is basically the least value for that particular condition to stay it in equilibrium.